Hi and welcome to Module 4.5 of Digital Signal Processing. In this module we will continue the exploration of the DTFT and we will consider in particular conditions related to its existence, its properties, and how we can look at it as a special type of basis expansion in the space of infinite sequences. So existence means simply that the sum that defines a DTFT does not blow up. This is easy to prove for absolutely summable sequences. If you take the magnitude of the DTFT at any point omega, this is equal to the sum for n that goes from minus infinity to plus infinity of x of n times e to the minus j omega n in magnitude. Now, every time you have the absolute value of a sum, you know that this is maximized by the sum of the absolute values of the elements of the sum. So we do this, and because the magnitude of the complex exponential is 1, this is actually equal to the sum of the absolute values of the sequence. Since our initial hypothesis was that the sequence was absolutely summable, this is less than infinity, and therefore the DTFT exists for all values of omega. Similarly, we can invert the DTFT very easily if we assume absolute summability of the underlying sequence. As we showed in the previous module, the inversion formula is 1 over 2 pi times the integral between minus pi and pi of the DTFT times e to the j omega n in d omega. So we replace x of e to the j omega by the definition of the DTFT in here. And because of the absolute summability of the sequence, we can invert the summation and the integral. When we do that, we have the sum for k that goes from minus infinity to plus infinity of x of k times this integral here. So each element of the sequence in the sum is multiplied by this integral, which depends on k. But now look at the numerator of this fraction here. This is a complex exponential, and if n is different than k, this will span an integer number of periods in the minus pi interval, and therefore the integral will be 0. So what that means is that this integral is 0 unless n is equal to k, at which point all the elements in the sum will be killed except for x of n. And so in the end we have the result we're looking for. The DTFT looks exactly like an inner product in the space C infinity. If you take this inner product here between an infinite sequence and the sequence e to the j omega n, and you write the definition of the inner product, you get exactly the formulation for the DTFT. The problem here is that C infinity is not really a well-defined vector space. There are sequences that do not converge in C infinity. Nonetheless, if we manage to establish a formal parallel between a change of basis and the DTFT, it will mean that everything that we discovered about the DFT, which is a well-defined entity, will apply to the DTFT as well, and all our intuition about the frequency domain will translate to the DTFT. Now, the basis here that we're talking about is not really a basis, because it's an infinite and uncountable set of vectors, indexed by a real-valued variable omega. So something breaks down really. We start with sequences, but we end up landing in a space of functions. On top of it all, although we just proved existence and invertibility for absolutely summable sequences, in reality the DTFT exists for all square summable sequences, which is a larger set of sequences. But in that case, the proofs we just gave become much more technical, and so we will skip them here. Let's sum up the situation so far. For finite length signals, we start in Cn, and via a change of basis, we compute their representation in the frequency domain, which as well lives in Cn. We can go back to the original sequence via the inversion formula, and the basis that allows us to go from the time domain to the frequency domain is the DFT basis, the Fourier basis for the DFT, which is a countable set of n Fourier basis vectors. The DFS is exactly the same. The expansion and reconstruction formulas are the same, except that in this case we assume that everything is periodic underneath. And now we have the DTFT. We start from the space of square summable sequences, and via a formal change of basis, so basis here is in quote, we end up in the space of square integrable functions on the interval minus pi pi. By looking at the DTFT as a formal basis expansion, the linearity property follows easily from the linearity of the inner product. So the DTFT of a linear combination of two sequences will be the linear combination of the DTFTs. A second property that is easy to prove from the definition of the DTFT is the time shift property. So if we take a sequence and we shift it in time by big M samples, the DTFT of this shifted sequence is equal to the DTFT of the original sequence times a delay factor e to the minus j omega big M, which is very similar to what we obtained in the case of the DFS when we took the shift of a periodic sequence. The dual of this property is the modulation property of the DTFT. So if we take a sequence and we multiply this by a complex exponential at frequency omega 0, what happens in frequency is that we have a shift of the spectrum by omega 0. The time reversal property tells us that the Fourier transform of a time reversed sequence, a sequence where we flip the values across the origin, will be equal to a frequency reversed Fourier transform. And the conjugation property says that if we conjugate every value of the sequence, the Fourier transform will be both conjugated and frequency reversed. Now, some particular cases that are very useful to remember because they appear often. First of all, if the sequence is symmetric, then the DTFT is symmetric as well. If the sequence is real, then the DTFT is Hermitian symmetric. Reality of the sequence can be expressed mathematically by saying that x of n is equal to the conjugate of x of n. This in frequency implies that the Fourier transform of the sequence is equal to the conjugate and frequency reversed version of the Fourier transform. A simple corollary of this property is the fact that if x of n is real, then the magnitude of the DTFT is symmetric. You can verify this simply by taking the magnitude of both terms of this equation. And an even more special case states that if x of n is real and symmetric, then x of j omega is also real and symmetric. So this all looks nice and fine. It looks like we have a full-fledged basis expansion and that the DTFT is just another version of the DFT. And indeed, some things would lead us to believe so. For instance, if you take the DFT of the delta function, you remember you have the constant 1. And similarly, the DTFT of the delta function, expressed as the inner product between the pseudo-basis function and the delta function, is again 1. However, some things are not okay at all. The DFT of the constant 1 is very well defined, and it's equal to n times the delta function in frequency. But the DTFT of 1 is, by definition, the sum from n that goes from minus infinity to plus infinity of e to the minus j omega n. Now, to see that there is a problem with the sum, just put omega equal to 0, and you see that the sum diverges. The problem is that there are too many interesting sequences that are not square summable, and of course the constant 1 is one of them. So in order to be able to keep using the change of basis paradigm, even for sequences that are not square summable, we have to introduce a little mathematical trick called the Dirac delta function. This little animal here, which is usually indicated by the symbol delta, but now delta of a real variable t, not the delta sequence, is defined by the sifting property that looks like this. If we take a delta function, we center it in S, where S is a variable in R, and then we multiply this delta function by any function of a real variable t, and then we take the integral from minus infinity to plus infinity, then what we get is the value of f in the point S. Graphically, we usually represent the delta function as an upwards pointing arrow. We center this in S, we multiply this by any function of a real variable t, and then we integrate this from minus infinity to plus infinity, and we get the value of the function in S. In order to develop some intuitions for the properties of the Dirac delta functional, let's consider a family of so-called localizing functions, Rk of t, where k is an integer index and t is a real valued variable. The properties of this family of functions are two. The support of each function is inversely proportional to the index k. But regardless of the index k, the area of each function, the integral from minus infinity to plus infinity of each function, is constant. As an example, take the rect function. The rect function is a classic indicator function that is equal to 1 from minus 1/2 to 1/2 and 0 everywhere else. So this function has a support of 1 and an area of 1. We can use this function to build a family of localizing functions like so. We multiply the rect by a factor k, and we shrink the support of the rect by a factor k. So rk of t in this case will have a support that goes from minus 1 over 2k to 1 over 2k. So the support is 1 over k, and the area is 1. If we plot some functions in this family, this is what we get for k equal to 1. The value here is 1. For k equal to 5, the support has shrunk to 1 over 5, and the area is still 1 because the value here is 5. We go to 15, it will look like this, and to 40, it will go like this, and we can go on to infinity. Now consider the integral between minus infinity and plus infinity of the product between rk of t and any function f of a real variable t. Rk of t is non-zero only between minus 1 over 2k and 1 over 2k. So these are the new integration limits of this product. The value of rk of t over the integration interval is k, so we can bring this outside of the interval. And inside we have simply the integral of the function over this interval. Now we invoke the mean value theorem. You can go back to your calculus textbook to revise its proof. And the mean value theorem says that the value of this integral here will be equal to f of gamma for some point gamma within the integration interval. Now we don't know where gamma is inside this interval, but we do know that it exists. Now as k goes to infinity, the support of the indicator function becomes smaller and smaller. And so gamma, which is somewhere in the integration interval, will be sandwiched between interval limits that grow closer and closer. And in the limit, f of gamma will be f of 0 because the width of the interval has shrunk down to an infinitesimal width. So the delta functional is really a shorthand for this limiting operation. Instead of writing the limit of the integral for a family of localizing function, we just use the delta notation. And what is interesting is that the shape of the base function that we use to build the family of localizing function is not really critical. We can use pretty much any shape, and as long as the two properties of shrinking support and constant area are satisfied, the limit will converge to the pointwise value of the function. Okay, so now a last technicality before we understand why we're doing all this. We will be using the Dirac delta functional in the frequency domain. Now we know that all DTFT spectra are 2π periodic. So if we want to use this tool in the frequency domain, we have to periodize it. The periodic version of the Dirac delta functional is called the pulse strain, and it is built by placing copies of the delta function every 2π and by scaling the whole signal by 2π. So if we want to represent that in the frequency domain with the usual upward arrow notation, we see that there will be a pulse every 2π. Okay, now we can let the show begin. Let's consider the inverse DTFT of the pulse strain. Well, we apply the definition and we have 1 over 2π times the integral between minus pi and pi of the pulse strain times e to the j omega n in the omega. So the first thing to remark is that since the periodized delta is scaled by a factor of 2π, this cancels the normalization factor in front of the integral. Then we are integrating only between minus pi and pi. In this interval we only have one pulse, so we can remove the implicit periodization. And then, because of the shifting property of the delta functional, this integral will be just the value of this function of the real valued variable omega in 0, because this delta is centered in 0. And so the value of e to the j omega n for omega equal to 0 is equal to 1. This is formally similar to the fact that the inverse DFT of n delta of k is actually equal to 1. So by using the delta functional, we have established another formal parallel between the DFT and DTFT. So if the inverse DTFT of the delta functional is 1, then it means that the direct DTFT, the forward Fourier transform of the constant 1, is formally equal to the pulse train. Does this make sense? Well, we could try to compute numerically the partial sums that are involved in the computation of the DTFT of the constant 1. So define sk of omega as the sum that goes from minus k to k of e to the minus j omega n. As k goes to infinity, sk of omega should converge to the DTFT of the constant 1. So if we plot these partial sums in magnitude for increasing values of k, we have something like this. For k equal to 5, we have this shape, and as we increase the index, we see that this family of partial sums looks like a family of localizing functions. So the support gets narrow and the area stays constant. So it really makes sense to say that in the limit, these partial sums will converge to the Dirac delta function. With this fundamental result in our pocket, we can now proceed to derive some other interesting DTFT pairs for non-square summable sequences. With the same technique we used before, we can show that the inverse DTFT of a shifted pulse train, a pulse train shifted by a frequency omega 0, gives a complex exponential of frequency omega 0 in the time domain. So if the DTFT of 1 is the pulse train centered in 0, the DTFT of an arbitrary complex exponential of frequency omega 0 is the pulse train shifted by omega 0. By using Euler's relation and the linearity of the DTFT, we can derive the DTFT of the cosine of omega 0 n. This is just 1/2 times the sum of two pulse trains, one centered in omega 0 and the other one centered in minus omega 0. And the DTFT of the sine of omega 0 n, which is minus j over 2 times a pulse train centered in omega 0 and another pulse train centered in minus omega 0.